Every Nest.js application has at least one module, a root module. The root module is the starting point Nest uses to build the application graph, which is the internal data structure that Nest uses to resolve module and provider relationships and dependencies. In this directed graph, in which the edges have a direction, every module is effectively represented as a single node. Importing another module or node instructs the Nest framework to create an edge between these 2 points in the graph. Although this graph is statically scoped and doesn't get recreated over time, meaning that only a single instance spans the entire application's lifecycle, it is possible that it may contain modules or nodes that register non-statically scoped providers, specifically request-scoped providers. Request-scoped providers get instantiated dynamically upon receiving a signal. In terms of, for example, REST APIs, this signal would be an HTTP request. However, for things like cron jobs, this signal will be the invocation of the job itself. You can see that when it comes to how request scope providers are invoked, it really depends on the context of an individual application. In reaction to that signal, Nest.js constructs a so-called dependency injection subtree that's associated with the given signal. For instance, for an incoming HTTP request, it instantiates a new controller that declares a specific route. This instance is created exclusively for that particular request, and will be removed when the request processing has completed. In this lesson, we'll showcase how you can manually construct and manage your own dependency injection subtrees using the power of the ModuleRef class. So, let's switch to our IDE, and using the Nest.js CLI, let's generate a new resource called tags. With this resource in place, let's navigate to the auto-generated tag service class and make it request scoped, passing in scope.request object to the injectable decorator. As we already learned in the fundamentals course, scopes actually bubble up the injection chain. This means that if the tags controller depends on the tag service, which is now request scoped, it implicitly becomes request scoped as well. Alright, next up, let's open the tags module file and inject the ModuleRef provider using the standard approach. Let's also make the tags module class implement the onApplication Bootstrap lifecycle hook. Our IDE should prompt us to implement that interface, so let's go ahead and do it. Inside of this onApplication Bootstrap method, let's dynamically resolve the request scope tag service provider using the ModuleRef and its resolve method, and let's console log that service out. Note that this resolve method may come in handy when testing request scope providers in the future, so always try to keep it in mind. Let's save our changes, open up our terminals, and as we can see here, our tag service was instantiated properly, just as we should expect. Great. Back to our task at hand, let's talk about what exactly happened here. So, what the ModuleRef.resolve method does under the hood is that it internally constructs a dedicated dependency injection subtree where our tag service is the root node of that tree. This subtree has its own unique context identifier that represents that tree. To better understand that, let's create 2 copies of the tag service provider calling resolve twice and comparing their references. And as we can see in our terminals, they are in fact not equal. So as we've mentioned above, the resolve method returns a unique instance of the provider from its own DI container subtree. These instances are not equal as they belong to different trees. To generate a single instance across multiple resolve calls and ensure they share this same generated DI container subtree, we can pass a context identifier to the resolve method. First, let's use the context_ID_factory class to generate a context identifier. This class provides a create method that returns an appropriate unique identifier. And with this context ID in place, let's pass it in as the second parameter of the resolve invocations. And if we save our changes and take a look at our terminals again, we'll see that our instances are now equal, hence true. Great. All right, so we already know how to generate context IDs, IDs that represent our subtrees, and the actual DI subtrees, using either a specific context ID or the auto-generated one. We also know that request scope providers can inject a request object, aka signal payload, that's associated with the host DI subtree. So for demonstration purposes, let's navigate to the tag service class and inject the request there. Let's also make sure to console log the request out. Next, let's switch back to the tags module file, and to make things simpler, let's make sure we create only one instance of the tags service. And now, for demonstration purposes, let's register a request payload for our subtree using the register request by context ID method as follows. Let's save our changes, open up our terminals, and voila! There's our request object, aka signal payload, that's successfully associated with the host DI subtree. Lastly, just a few more important notes about the context IDs. In fact, a context ID is just a regular unique JavaScript object. Nest.js associates subtrees with their corresponding ID objects, and if the context ID gets garbage collected, so does the entire DI subtree. That means DI subtrees are ephemeral, meaning that they are removed as soon as their context ID is garbage collected. Just keep in mind that if you keep track of the context ID, for example, by storing it in the static array or any other collection, the subtree associated with that context object will never get removed. Great, so now that we have an understanding of the basic mechanics of DI subtrees, let's dive into a bit more practical example in the next lesson.